Hey, so today it's Saturday. It's quite rainy outside. I've got my cup of coffee here, and we're going to continue what we started. Last time we talked about dependent pair types, and then we used that to implement something, well, to formalize the Ekman-Hilton argument. Today, I want to go and talk about the most classical or the most popular or most well-known example of an inductive type, which is the natural numbers. So just before we get started, uh, just last time, as I said, we talked about dependent pair types. So Lean has a special syntax to talk about these, and it's called the structure keyword. So if I want to build some structure, let's say last time we consider magma, I can write structure magma where, and then here I will put all the fields that are in this structure. And this implements basically what we did with dependent pairs, but there are many advantages to this syntax. For instance, in dependent pairs, we were obligated to iterate like if we wanted to talk about magmas, we had to talk about the underlying set, which was the first thing in the pair, and then the second thing was another pair. So we had to iterate like that. The structure keyword makes it easier to do this kind of stuff. So it's quite useful. Yeah, I won't really dwell on this. I just want to mention it, but you should, I mean, if you're basic passage only, if you know a bit of Lean already, you already know what the structure keyword is, so I won't dwell on it. So today we'll talk about the natural numbers. We'll define them as such, and then the natural numbers are quite interesting. They are these like simple example of inductive type that is truly inductive in the sense that one of the constructors, the successor, will depend on the type it's attached to. The first constructor is just 0, which represent the natural number 0, right? And then, yeah, I hope you can hear this crazy music outside. The successor now is sorry, I changed keyboards again. Okay. So here we have the type of natural numbers, and this is, we can do arithmetic with this, which is quite crazy if you think about it. But under the interpretation where every constructor will freely generate the type, we can see natural numbers as the smallest type, freely generated by these two here. Now using these, we may want to prove some theorems. Well, first we would like to do some constructions, and then we would like to prove some theorems about these constructions. The first construction that I would like to do is the obvious one, which is the sum of two natural numbers. Sorry, like I said, I changed keyboards, so it's kind of weird, but we have addition of two numbers, and this is a function that takes two arguments and spits out their sum. Now there's a special syntax here that we can use to, because we have no other choice than doing this definition by induction, right? Using the recursor. Like I mentioned in a previous video, the recursor is the only way to build functions out of a type we've defined, and right now we're trying to define this function. So just for fun, right? We're going to define this one using the recursor. So we need this. Yeah, again, just for fun, because we like to have weird fun, we'll specify explicitly what the motif the motif here is. Oops. So let me remember. The motif. Okay, we'll take one argument like that, and we need to produce a type here. So for every natural number, what we will actually define is a function that takes another natural number and that spits out the function that, well, so the type we want to build is this. Let me just do this. Yeah. Okay, that's sorted out. Now the first argument is what should add 0 be? Well, add 0 should be a function that adds 0 to a number, and we expect that to do nothing. In other words, we expect that to be the identity function. So I'll just write that here. I have some stuff is happening. Let me just check something real quick here. Yeah, exactly. Okay. So you see the expected type here is basically just this. And I want this to be the identity function. Yeah, that works. Yeah, that works. Okay. And now this one. So the expected type here is going to be a function that takes some natural number a, and which takes another function as a second parameter, and outputs what outputs a new function that should be adding one more. Okay, so let me write this clearer. So the first argument, as I said, is a natural number n, and the second one is some function f. What should we produce? We should produce some function here. And the idea here is that f is a function that adds n. Like it takes any number k. Let me write this. So f, it adds n to k. Let's say f applied to k is n plus k. Let's write it like that, that's clearer, right? And now we want a function that will do n plus 1 plus k. We want such a function, but okay, we would expect that to be the same as just doing this and then adding 1, right? So this is what we'll write here. I'll just put ourselves into the natural number namespace, so it's easier to type stuff, right? There we go. So we want successor f applied to n. What did I do? Oh boy. So, okay, f is the function which adds n, and what we want to do is construct a function that adds n plus 1. So f is the function that adds n, like I said, and we want the function that adds n plus 1. And we know that adding n plus 1 is the same as just adding k first and then adding 1. And we can do that using f of k. Right? So we can take here k as a new parameter and then do the successor of k. That should work. Yeah, and that should be the correct definition. If I didn't fuck up early, that should be the correct definition of adding two numbers together. Once again, like in my other videos, you know, there's here we need non-computable, since Lean expects to be able to generate some code here, but we just want to use the type checker. We don't care about running actual code. Here I can, you know, these arguments are not used. Let's just get rid of them. Okay. So now we have a function which adds stuff. We would like to prove some theorems about it. What do we know about it? Well, first thing I would like to show is that it admits 0 as a neutral element. That would be pretty nice, I guess. I don't have a script here. I'm just thinking out loud into this microphone in English. And I think I would like to prove that 0 is the neutral element for the addition I just defined. So let's do that. Following the convention in MATLib, we will call this theorem 0add, which will say that adding 0 on the left is neutral, which is why the 0 here is on the left. That's a nice convention, you get used to it. So add 0 and anything should give us back the thing. Of course, yeah, n should be implicit parameters, but I have the option of auto implicit parameters enabled, so as you can see, Lean helpfully adds this here. Let's prove this. We can prove this in many ways. It's quite simple, so maybe we can just do it by reflexivity, actually. Yeah, that's because by definition, you know, add here is just this, if we like literally replace it with this. And we know there are some computation rules that when you apply one constructor, here is 0, and you apply this constructor to a definition that is built using the recursor like that, we know this is going to be, by definition, this is just the identity function. And then what we're saying here is, okay, well, is it true that ID n equals n? Like, this is the same thing. This is the same theorem. And of course, ID n is equal to n just by the computation rules as well. So this is true by reflexivity. That's quite nice. That's easy. You know what? Let's add this to our simp lemmas. We're going to use simps. We also have that 0 is a neutral element on the right. I'm not sure if this is going to be as easy to prove as that, because it's not going to be true by definition, as you can see here, because we define add by recursion on the first argument. So it's going to be a little more complicated. So a way to work around this, or to do some more general maths, would be maybe to show first that the add function here is commutative. That could be nice. And then we would have add 0, like for free. Yeah, we could try this. I'm not sure it's going to work well, but could be nice to try. I don't really remember. I did this like a long time ago. All of this. But yeah, we can try it. Let's try. And sorry, this theorem is going to say that like any two number of a, b, this is going to be equal to this. And yeah, I'm not sure if we're going to be able to just prove it like that. Could be that we need more lemmas. Let's just sorry that for now, okay? Because I'm just thinking maybe we should prove that it's associative first. You know, if you think about it, like the first thing we would like to have is that it's a group, and you know, when you have some algebraic structures like groups, well, the associativity comes first. It comes before commutativity. So here I expect that associativity is going to be easier to prove. Let's just try it again. And oops. And once again here, lean is going to really helpfully put some auto implicits here, which is nice. I like this. I like this because I feel like I can write more freely what I want before thinking about what's going to be, like what's going to go in my statement. Like here, if there wasn't these, I would have to write first, okay, for all ABC, we have this. But when I write math on paper, every time there's a variable that appears without the quantifier, it's kind of like implicitly with the for all quantifier, you know. So this is nice. Okay. So I'd like to prove this. Actually, I'm seeing that, you know, add is defined by recursion on the first parameter, so maybe this would be better here. It doesn't really matter. Maybe it's just technically more easy or easier. Okay, so to prove this, we could use the recursor. We could also use pattern matching. So I actually think this we'll use pattern matching here, just to see. Yeah, so pattern matching is basically syntactic sugar over the recursor. So we're going to not deprive ourselves of this anymore. Like before, I consciously avoided using the match statements because I wanted to talk about the recursor like really explicitly, but you know, now let's use it. So okay, we can match A, and every line in the match statements, sorry, every line in the match statement corresponds to one explicit parameter to the recursor. Here, our recursor, as you can see here, it has first parameter corresponds to 0, and the second one corresponds to the successor. Okay, so what happens when A is 0? That's basically all that I wanted to say. What happens then? Well, let's just sorry that. And where's I'm having trouble finding this pipe character on my keyboard for some reason. So we could also have that A is the successor event. Okay. So here, let's actually put a hole here. We see the statement. It's actually we need to show that 0 plus b plus c is the same thing as 0 plus b plus c. But notice here we have 0 add, and we proved that this is the same thing as just add, right? It was just reflexivity. So we know this is B, and same for here. We know this is so okay. If this is B, this is going to be the whole thing here is going to be just B plus C, and the whole thing here is going to be just B plus C as well because of zero add. So I'm thinking I can just do this like that and let Lean compute it, and yeah, I'm right. So this is the proof in this case. Now we go to the more complicated case. Okay. What's going on here? Maybe we would need to do like induction inside the induction. That's possible as well. I really don't like having this this field notation in this case. So pretty print point field notation false in. Okay. Yeah, I much prefer this in this specific case here. I think it's way cleaner. And yeah, let's see. So by definition, we know that this. Okay, I'm just going to do a little math here. So by definition, we define this to compute into the successor of add and C, right? This is just our definition here, which says that to compute what adding n plus 1 is, well, you just add n and then you add 1, right? This is just by reflexivity. And now, okay. Once we have this, you know, and what we want at the end, what we need to find is this here. We want this. So how do we fill in the details here? Yeah, I'm actually not sure. Let me think about this for a moment. It's always harder to do math in front of a camera, or I guess an audience. If anyone is watching this, say hi. So it's like it's as if the successor here gets sent into the two parentheses here, which is interesting. I'm not sure. Maybe if we were to do an induction on this bad boy here, could be useful. The only thing I'm noticing really is that here B is the first argument to add, which is good when we want to do stuff using induction. Okay, but here I'm noticing that B is the second argument of add, which is not that great. However, oh yeah, I should have noticed this quickly, but here we have add, and then the first argument is the successor of something. So we know, again by reflexivity, but by definition, that this add inside is going to be written like that. Oh yeah, that works. Okay, so this is add and B, just by definition of add, and then we have C. Now notice that the first argument here has become a successor as well. And just this step is by reflexivity as well. So there's nothing to prove, it's just, yeah, we don't have to figure out the proof for this. Is syntactically the same for Lee. And for the same reason here, like the definition of add, when the first argument is a successor, we just get add, and then add and B, and C. And again, this is by reflexivity. But now, notice that this is equal to this. Almost. It's not. It's not equal. It's almost equal. It's almost equal. But this is equal to this by the induction hypothesis, which says that our addition is associative when n is for n. We're trying to prove it for n plus 1, and we know by the induction hypothesis, we know this is equal to this. Okay, and if we come here, I'm not sure, we don't have, it doesn't seem like we have this induction hypothesis in the context. Let me just, I'm not sure how to get it. Yeah, I guess we need to do proof by induction actually. Yeah. I hope this music is not going to get my YouTube video copyrighted. It's not mine. It's just playing really loudly outside. Like really loudly. I'm not sure, I feel like I'm confused. Because I thought that the match statement would just get compiled into the recursor, and when you prove stuff using the recursor, you do have access to the induction hypothesis. And here I'm not sure, I don't see it in the, I don't see the induction hypothesis in the local context here. So maybe if I just replace this with induction call. Well, let's put ourselves in the tactic mode first, and then we'll do induction on A. I would like to introduce some names as well. Let me just read the documentation real quick. Yeah, so I kind of want this syntax right here. And this is exactly what I want actually. So I just need width, and then there's the 0 case. I just put a hole here, but we know what goes here. It's just reflexivity. Let's put it like that. It's nicer like that. And then it's the successor of n, and there's our induction hypothesis. If I'm not mistaken, here we can use, we should have, yeah, we do have our induction hypothesis here in the local context. I'm just wondering if here I'm still in tactic mode. I'm just going to read the documentation real quick. Yeah, as you can see, it says here use tactic, tac1, and so on. So here I'm actually still in tactic mode. So yeah, I see I have this induction hypothesis here. And by what I wrote here, I know that everything here, like this is equal to this line here, or this segment of line here is equal to this, just by reflexivity. And this, I can tell Lean that this is the new thing I want to show. Or, how can I say? I want Lean to rewrite stuff by, I guess I can do change. Yeah, as you can see, change A with B will change the occurrences of A to B in the goal. assuming A and B are definitionally equal. Yeah, and this is what I want. I believe I could also use show. Show does more things, you know, it tries to unify stuff. Let's try show. I want this is equal to this. Yeah, and this is the new thing I need to show. I'm not sure how to indent this. Let's just do it like that. Okay, so this is it's not the new thing I want to show because it was always this. I just massaged it in a way that means I can use the induction hypothesis here. And this is what I was saying, like this is equal to this by hypothesis. I could prove this by two ways. There are, or at least two ways. One I like is when you have constructors like that, you can use congruence, the congruence tactic. Okay, so now it's saying everything is fine, but let's say I just want congruence 1, and yeah, okay, nice. So I guess I just wanted to show what the goal becomes when I use the congruence tactic, but it looks like it automatically uses assumption as well. But what is happening is after congruence tactic, the new goal would be to prove what is inside here is equal to what is inside here. But then the congruence tactic automatically applies the induction hypothesis because it's in the local context, and it closes the goals by itself. So, you know, another way would be to just rewrite and just rewrite like that. Maybe that's even easier, I don't know, or simpler. There you go. So we actually have shown that addition is associative. That's cool. Not sure we want to add that to our simplemmas. So just going to delete all of this. Now I feel like we're ready to prove commutativity. So we also are going to prove it by induction on A, which is the first argument on the left. Maybe here it's nicer to have it like that. Yeah, it doesn't matter. Okay, in the case where we have 0, we need to show that add 0b is the same as add b0. So now I'm seeing that this base case here in the induction problem would be easier to solve if we had already proven that add 0 is true. Like here we have 0 add. We would like to have the other way around. I know that I said that we could use this to prove add 0, but now I'm noticing that the base case is going to be easier, I think, if we do it like that first, and then generalize, and then use this to prove commutativity. Okay. And now, as you can see, it doesn't work to use reflexivity, right? It just doesn't work because it's not true by reflexivity anymore. We need some more. We need to grind a bit more. Let's grind. So we're going to prove this by induction as well. Let's put ourselves in tactic mode. I quite like tactic mode. It's nice. I like it. It's really nice. It's chill. Okay, induction on n. When n is 0, this is easy because it's just add 0, 0, and this is equal to 0 by our theorem here. So I'm just going to say this is exactly 0 add, right? And that works. You know, it says no goals, everything is fine. The tricky part should be the induction step. So when we have something like that, right? Here, what we need is I don't know why it says no goals. I'm not sure. Okay, anyways, we have unsolved goals here. This is our local context. We know that, okay, once again, let me just let me just remove field notation for the whole file, because this is annoying me. Okay. Okay, so once again, we want to show this here. Usually I just do it quickly on, I would just do this quickly on paper, but you won't see my paper. So here, this is what we want to show. So we should have, you know, some steps in between before we get to this. Once again, when the first argument is a successor, by reflexivity, we know this is the same thing as just adding n and 0 and then taking the successor of this. And we know this is equal to n by the induction hypothesis. Okay, this is nice. So it's really not hard at all. We're going to just rewrite quickly the goal using here we use show. Now let's try to use change. Okay, change. No, okay, I won't use change because it asks for like what. Yeah, okay, sure. So we will change something in the goal. You know, here the goal is this, and we know this expression here, it's differentially equal with successor add n 0. And I forgot with. Okay. Okay, well, listen, I'll just. Please, Lean, I'm not understanding what's going on here. I'll just use show. I want to show this is equal to successor of n. Yeah, that's better. Okay. And you know, notice I didn't need to provide a proof of this, like to change the goal. You see here I'm pointing the screen, that won't work. So, you know, this was the goal before, now the goal is this, and I didn't need to provide a proof because these two things are the same in the eyes of Lean, and that's a very important point. Anyways, to prove this now, you see we can simply use the induction hypothesis. I could use the rewrite tactic just as I did here. I could also use congruence and prove it. Excellent. So now we know adding 0 on both sides does nothing, that's fine. We can use this to prove the base case of our commutativity theorem, because by the 0 add theorem, this is just B, right? And by the add 0 theorem, this is just B as well. So if I decide to add this to our simp lemmas, here I can just do by simp, and I'm already in tactic mode, but I can just do simp, and it's going to find these. A way to verify this is just to put this question mark here. When you put this question mark, simp will print here what it uses. And yeah, and we can just like rewrite is simple enough. We don't need the whole power of the simp. Anyways, and when it's the successor, in the successor case, this is what we need to prove. Once again, I'll just begin a simple comment here. Okay, this is what we want to prove. Eventually. Yeah, okay. And we know couple of things. First, by reflexivity again, or by definition, going from the first line to the second line is just by reflexivity. Okay, so let me just keep this pause. Okay. And you know, once we're here, we know by the induction hypothesis that this is going to be we can commute those, you know, by hypothesis. That's good. And then to go from here to here, this is simply again an implication of the reflexivity, because this is equal to this by definition. We actually have a proof, and when I write this, like Lean actually almost understands this. This is the calc. Calc. I can start with what I want to show, which is add sub n b, and then I can like write it in steps, just like I did. So if I remember, this is true by reflexivity. What's going on here? Yeah. This, like, you in the calc block you need to justify every step, like I did. Add b n, and this is by induction hypothesis, or I could just write this like that. It's not liking it. What's going on? Oh yeah. Let's just do a rewrite, okay? Going to make it happy. And now we know this is equal to successor of n. Wait, what am I doing here? That doesn't work actually. Yeah, that's kind of annoying. That doesn't really work, does it? That doesn't really work, because here, going from this line to this line, yeah, it's not it's not the same thing, because here the successor is going to be applied to b, and want it to be applied to n. And that doesn't work at all. Let me think about this for a moment. You know, when trying to prove something about addition, you can feel a bit dumb when you're not finding the proof quickly enough. It's okay. Yeah, so I feel like we have to use like associativity. I do feel like we have to use associativity here. Yeah, I see. So if we knew, like, the successor is basically just adding one, right? So suppose we had some theorem that said exactly that. Then we could, by reflexivity, the previous line, like the line just before my cursor here, would be equal to adding the successor of b with n, right? And then, provided we have a theorem that says that the successor is just adding 1, we could rewrite this as adding like successor of 0 is 1. So they just say it like 1 b n. We'd have something like that, and then we could use, or no, it would be better to have it like that, right? Yeah. And then we could rewrite this as just b add 1n by associativity, right? Oh my god, the music is so loud outside. Oh my god, this is terrible. Okay. Anyways, okay, so we would have this, and you know, we would need a theorem that says this as well is equal to the successor, and then we would win, right? Okay. My goodness. I hope the noise suppressor is doing its job correctly. So otherwise I'm going to get copyright striked or something. Okay. So we would need a theorem that says that adding 1 on both sides, right, is just a successor. That would be enough to prove what we need. So let's do it. Let's call it suck is add 1. I don't know. And the type of this is that successor of n is adding 1 to n. And of course 1 here is the successor of 0. Okay, so how to prove this? Well, by induction, of course. So in the case where n is 0, we want to show that 1 is equal to 1. You know, we have a theorem that says adding 0 just gives you back the same thing. So I reckon that if we just do rewrite 0 add, then it's going to prove that thing, and it does. Okay. And once again, in the successor case, it's more complicated, but not really that more complicated. So here we know how this goes, right? This is going to be the successor of add n 1. Okay, let me just open a new comment. Where's my... Okay. This is what we want to show. And this here, we know this is equal to the successor of add n, and then 0, 0. And we have the induction hypothesis, which says that you know, this here, which is contained in the parenthesis here, this is just equal to the successor of n. So it's going to be quite easy to prove. But let's just use a change command again. I'm not sure it's needed, but whatever. Or no, okay, we can use the calc block again. So a good thing would be, like, we start with what we wish to show, and then this is equal to add n 0, just by rewriting the induction hypothesis. And this is equal to add n 0 by reflexivity. Okay, so we have this. That's great. That's quite nice. Now we would need, because here, you know, we are adding 1 to the right. Now we would need to add 1 to the left as well. So theorem is 1 add. Okay, this is adding on the other side. So notice we're proving a very special case of commutativity. And here this is basically proving a very special case of commutativity when we're adding 0, and now we're proving it when, in some way, like when we're adding 1. Let's add, or maybe it would be more insightful to say that we're showing a theorem, how our general theorem here works for the constructors, right? And then the general theorem will bundle everything together and give us a result for everything. So 0 and so here, and I'm thinking here that the first thing I would like to do is have this flipped around. I think it would be easier, but I'm kind of lazy and I don't want to rewrite this proof so that it works. So there's a tactic that's called sim, which will just do this flipping around, as you can see. Now we can use just the fact this is equal to the successor of add 0 n. And then we know that adding 0 and n just gives you n. So this is going to be provable using rewrite 0 add, I think. No, it's not. Really? Okay. I'm not going to fight you too much here, Lean. I'm just going to say this is what I want to show, and then I know that inside here, like 0 add gives me 0, and that works. That's fine with me. Okay. So let's go back to our commutativity proof. We know that to get from this line to this line, this is just reflexivity. So that's nice. But now to get from this line to this one, it's a bit more interesting, right? So this is add the 0 and by, and no, this is what we want to show here. And if we go to what we just proved, which form is it? So it's 1 on the right. So it's this one here. It's this one here that we need. I'm just going to rewrite using this. Yeah. Now this is simply add 1 and n by associativity. It should work like that. Yeah. Now we're almost done. So adding 1 is just a successor event, and this is by is 1 add, and doing it in the reverse direction, and we're actually done. Yeah, we're done. So I can just delete this comment real quick. Yeah. So this is a proof that addition is commutative. Cool. That's cool. Yeah. I mean, it's quite. It feels like the first time I had to prove that addition was commutative, I felt like I was stepping backwards in my mathematics education, but we're actually stepping forwards. So I'm just checking the time here. I'm noticing this is exactly 55 minutes and 4 seconds. This is quite long for a video. I'm thinking maybe I should stop here. Just having fun with the natural number type, but you know, maybe as an exercise, if anyone is still listening at this point, which I highly doubt, then you could try to define all the other arithmetic, classical arithmetic functions, you know, like subtraction, multiplication, division, etc. Just a little spicy something that we're actually trying to define stuff with the natural numbers, so there's no negative numbers. So if you try to subtract a bigger number from a smaller number, you should get 0, like it should clip at 0. It's interesting. There's actually some categorical mathematical justifications for this clipping at 0, but it also kind of makes sense to clip at 0. But then this will mean that, you know, subtraction is not actually the inverse of addition in all cases and stuff like that. Whatever, this is trivial. And also a little supplementary spicy thing is that division by 0, it makes more sense and lean to actually allow to divide by 0, but just you know, just set it to be equal to 0. And then when we will prove theorems about division, we will require one of the hypotheses to be that the denominator is not 0. This is actually a kind of cleaner way to do stuff. It's not like a contradiction or anything like that. Just say that, well, division is a total function instead of a partial one. And then you move the requirement that you can't divide by 0, you move that requirement to the theorems that actually use division. It kind of, when you think, it seems weird, like the first time you hear about dividing by 0 gives you 0, but it kind of makes sense from a, it's the same thing and it's more pragmatic. Okay. We actually, I want to say maybe a last something before I close this video, is that we can implement some notation here. We could use the plus symbol for the add, like we do an instance of, I think, how was it called? I think just add. Okay, let's do it like that. And you see here we need to put add. Sorry, and just add like that. Okay, there we go. And this means now we can do stuff like 0 plus 0 equals 0, and or just like that. This is going to be an element of our type because we implemented this thing. There are also other stuff, like I think, how was it called? Has one, something like that, or just one. Yeah, just one. This is a class that says, okay, there's an element called 1 and is the successor of 0. There's also 0. Of course, this is going to be 0. So now we can do stuff like write this, and I expect this to type check, and you know, I also expect this to type check. However, this would not type check because, you know, we said, okay, there's a 1 and there's a 0, but we would need to actually make an instance for, let me just keep this, we'd actually need to make an instance of not, right? And then I'm not going to do it, but we could have like the usual notation. So yeah, this video is long enough. We're just having a bit of fun with this particular inductive type, which is supposed to represent natural numbers. We've seen how to make a construction, which is add here. Constructions, in this case, this is just a function from natural number into this function type. And we've seen how to use induction to prove stuff about this construction that was made using the recursor. The last thing we've proven is that addition is commutative by showing that it commutes on 0, which is the first constructor, and by showing that it commutes on 1, basically, and then showing that this goes through for every natural number in this chain of reasoning here. So I hope if anyone is listening that you find this interesting. Say hi in the comments or something. I do like to make videos about Lean. I do think that it's going to get big in the future, and I hope to make more. I'm thinking of like not implementing, but I'm thinking of doing a last video in this series where I would talk about an important inductive type which subsumes almost all the others that we've talked about, which is the W types, which are the W types. So yeah, maybe I'll talk about this in the next video, and take care, have fun, have a nice day. Bye.